So, good afternoon. And today's goal is to wrap up semiconductor theory. And from next week onwards, we'll get into devices and then circuits. But I want this to be the last class where we just delve into semiconductor theory. We've looked at P-type semiconductors, N-type semiconductors. Today, we're going to look at what happens when we join both of them together. Okay, so let's bring up the notebook. All right, doping levels, electrical conduction semiconductors, and here. All right, so we have a P-type material with with extrinsically generated holes,
don't you?
and we have N-type material. N-type material with extrinsically generated electrons. So we would expect that this semiconductor material being charge neutral, you would expect it to behave like a resistor, right? So if you apply voltage to a resistor, current will increase or decrease linearly, right? So resistor is a linear device, meaning the relationship between the current and voltage is linear. So you would expect that to happen when you connect P and N-type material too. But that's not actually what happens, right? Expectation would be that it might be linear, but when they first created these diodes and semiconductor devices, they discovered that the relationship between the voltage and the current was non-linear. It's evidenced by here. Okay, so this is positive voltage, positive current. They discovered that there was no current flow through these devices until the applied voltage reached a certain level. And that is indicated by this thing right there. It's almost nearly equal to zero. Voltage increases, but current does not increase at all, stays zero. And then as the voltage starts climbing, slowly but surely, current starts increasing. But after a certain point, it's an exponential rise in the current. From that point on, a very small increase in voltage, millivolts, will cause a large increase in current. So the response was non-linear. Hence, these devices are non-linear devices. Okay. On the other side, if the voltage was decreased, well, decreased in the sense negative voltage was applied, not V minus, minus V and minus I, there was absolutely no current flow for a long range. And then after a certain point, the voltage crossed a higher limit and the junction breaks down and there's a huge increase in the amount of current that's flowing, which had a near vertical slope or near vertical characteristics. Meaning the voltage could increase a very tiny fraction and the current would just increase beyond exponential. Okay, so that's what they discovered. So then they performed experiments and postulated theories as to what is actually going on inside the junction. So let's look at what's going on inside the junction. All right. So we have separate P and N type semiconductor materials. In the P side of things, we have excess of holes indicated by the circles. And on the N side, we have excess of electrons indicated by the dots. Okay. So if you bring a P and N type material together, you obtain, this is known as the junction. So refer to this as the junction. Okay. Excuse me. So when you bring a P and N type material together, what happens? Excess of negative charges on one side, excess of positive charges on the other side. There's a charge imbalance. And because there is a charge imbalance, they will diffuse through the junction in a bid to even out the charge dispersion, the charge distribution. Remember, previous class, we talked about diffusion current, where the charges diffuse through the material in a bid to even out the charges or evenly distribute the charges. If this phenomenon progressed unimpeded, you would have equal number of holes and electrons on both sides of the junction, right? But that's not what they observed. So the charges started dispersing, holes crossed over into the N-type, electrons crossed over into the P-type, and they stopped. So again, they performed experiments, and from their results, they postulated theories that what is actually happening is, well, what happens when an electron meets a hole? Recombination, right? So electron jumps into an empty spot, recombination occurs, and one positive charge and one negative charge is taken out, right? So two charges are going to disappear. So if electrons are crossing the junction, holes are crossing the junction, recombination occurs, a whole bunch of electrons and a whole bunch of holes, they all disappear. So those charges start disappearing. As the charges start disappearing, they're going to leave behind their ionized atoms, right? These are donor atoms, and these are acceptor atoms, right? And because they're already ionized, they have positive charges on the N side and negative charges on the P side of the junction. So as the free charges disappear, these fixed charges stay in place because these are atoms. They're part of the lattice structure. They're not going to go anywhere. So the free charge carriers that would result in the flow of current are now gone. Okay, they are now gone. But they have left behind these immobile or unmovable positive and negative charges on either side of the junction. When you have a buildup of positive charges on one side and a buildup of negative charges on the one side, it gives rise to an electric field. So effectively, there is a built-in electric field at that junction. And this electric field, which is noted right here, is going from right to left, from the N side to the P side, right? Always goes from high to low. Positive ions on the N side, negative ions on the P side. So again, electrons and holes recombine, leaves behind positive and negative charges, gives rise to an electric field. The imbalance gives rise to an electric field. This electric field is going to oppose the flow of further, so it's going to oppose the further flow of holes and electrons. Why? Because holes would like to move with the field, and electrons would like to move against the field. Electrons have negative charge, holes have positive charge. So holes like to move with the field, electrons like to move against the field. But in this case, what is happening is the electric field is in opposition to the majority carriers on either side. So the holes are forced to go against the field, and electrons are forced to move along or with the field. Okay, they're forced to move with the field. If it was reversed, if the electric field had the opposite charges, then the holes and electrons would keep moving. But in that case, the electric field would never exist in the first place. All right, let's take a pause. Think over that. Let me know if you have any questions.
I have it. I have a question.
Just a second. Okay, so there's an in-class question. I'll finish that and then I can answer online questions. Yes. So your question is this why we always draw P on the left and N side on the right? The answer is no. This is just an example. Could be anyone. Yeah. It's just we refer to P-N junction. So sometimes the explanation just becomes like convention. But we could just as easily have N type on the left side and P type on the right side. It still have exactly the same. So, and this, whatever we are discussing, what we are talking about right now, occurs naturally in all semiconductors, not just silicon, not just germanium, all. So it's a phenomenon that's observed in all semiconductors. Okay. All right. So somebody was talking online. Go ahead, please.
What do you mean by uncovered in this slide?
Okay, so uncovered, question being asked is about uncovered ions. That's a good question. Uncovered simply means it has lost its corresponding charge. So if you're a donor atom, the donor atom is donating an electron, meaning that atom is now ionized with a positive charge, which is right here, right? Ionized donor atom has a positive charge right here. If that ionized atom loses its electron, meaning losing in the sense electrons moved away, it's recombined with the whole. It's leaving behind one extra positive charge that simply is referred to as an uncovered or unmatched or mismatched charge or mismatched ion. That's what it means. So uncovered means it's unbalanced. It's not balanced with a charge on the other side. Does that make sense?
Yeah, thanks.
Okay. Yeah. All right. So as I was saying, so there's a built-in electric field. That electric field opposes any further diffusion of those charge carriers. And this phenomenon is observed in all semiconductor materials, in all kinds of dopant impurities, and in all doping levels. Okay, it doesn't matter what doping level it is, doesn't matter how many atoms we're introducing, light doping, heavy doping, it always ends up diffusing to a certain extent and then being blocked. Okay. And so the phenomenon that is occurring is what it's trying to do is it's trying to diffuse into the material until the point where the charge is electrically neutral. Okay, until the charge is electrically neutral, or the device overall is electrically neutral. So this junction that we see right here, or this region that we see, is known as the space charge region. Okay, space charge region. And in the space charge region, SCR, there are no free charge carriers. There are no freely moving charge carriers, right? The whole point of doing all of this doping and introducing is to create an extrinsic semiconductor. So we have an excess of free moving charge carriers. So in the space charge region, there are no free moving charge carriers. They are not free to move around. There is no charge carriers. It is completely depleted or devoid. And hence, this is very commonly known as the depletion region. Depletion region. Okay, the space charge region would be considered more technical term, and the depletion region is very typically used across all books, all authors. Whenever we're discussing semiconductor devices, we always use depletion region because it is depleted of all charge carriers. Okay. So let's model the space charge of the depletion region. Okay. For that, the majority and minority carriers. Okay. So in the N-type material, electrons are the majority carriers, holes are the minority carriers. In a P-type material, holes are the majority and electrons are the minority. So now, the reason the reason the diffusion stops is because of the nature of the electric field, right? The holes and electrons have to move against. They have to move against their natural instinct. So they require extra or external energy to actually move through the device. Okay. We want the holes and electrons to cross the junction, to move through the device. Because if they are not crossing the junction, if they're not moving through the device, then there's no current flow through the device. If the electrons and holes are going in the opposite direction, they're going out of the device, there's no current flowing through the device. So the whole goal is they should cross the junction and move through the device so that current flows through the device. Okay. When charge carriers move, we say current is flowing. So if the holes and electrons are separated by that depletion region, external energy must be imparted to those majority carriers for them to overcome the barrier and start crossing the junction. But we have minority carriers on both sides. Those minority carriers are attracted by that electric field because it's their natural ability, their natural intrinsic property to move with the field. And so the minority carriers are able to cross the junction. And because they are able to cross the junction, it results in a very, very tiny amount of drift current that is flowing through the junction. If you apply an electric field, a very tiny drift current flows the junction because of the minority carriers. Okay, because of the minority carriers. Okay, so, oh yeah, and most importantly, the width of the region automatically adapts. Remember, I just stated a few minutes ago, doesn't matter the doping profile, doesn't matter the concentration, doesn't matter the dimensions. It always, always, always stops after the charge is balanced out. Okay, so the depletion region will adapt itself so that the charge is completely neutral, meaning the net current is exactly zero. All right, so relative dimensions of the depletion region. Well, this is the junction right there. Let's call this 0. X is basically how far the depletion region extends into each side of the junction. Okay, X is the distance. X is the distance as to how far it extends on both sides of the junction. Now, the key point was it'll keep diffusing until the charges are balanced out on both sides. So if we have an uneven doping profile, meaning on the N side or the P side, if the doping concentration is higher on one side versus the other one, the distance of the depletion region from the junction is going to adapt to maintain and balance out those charges on both sides. As an example, here we say N type is 3 into 10 raised to 16 atoms per centimeter cube. On the P side, it's 1 into 10 raised to 16. So there are 3 times as many donor atoms as compared to the acceptor atoms. Okay. And so when the junction is formed, the charges keep diffusing through the material until the charge is distributed in an equal quantity. So if the doping concentration, meaning the electric field, is higher on the N side, it is going to occupy a smaller space versus the P side, where the doping concentration is 1/3 of the N side. And so it's going to occupy a larger space. Does that make sense? Right? And so we see that here. Oh, before that, sorry, I want to point this out. So the ratio of the distance xp to xn or xn to xp is always proportional to the doping concentration, the ratio of the doping concentrations, which is Na over Nd. Yes. That's, yeah, yep. The question being asked is about the diode forward voltage drop. And so in a few slides, we'll actually look at that, how and why it happens. Okay, so XP, the ratio of XP and XN is always equal to the ratio of the doping concentrations. So if we model or if we graph or we plot these, it looks like this. So here, number of charges higher, Q times ND and Q times NA, right? Area under the curve will always turn out to be equal. So if we model that, I'm going to have three quantities that we'll talk about. Okay. So we integrate the area under the curve, we get the total energy that is present in that junction. And that junction, again, the junction gives rise to an electric field. The total sum of Xn and Xp gives us the width of the depletion region. Okay, it gives us the width of the depletion region, which is indicated right here, WD0. That's the width of the depletion region, WD0. It is Xn plus Xp. Okay, Xn plus Xp. And integrate that electric field. And you can express that in terms of a junction voltage. This voltage is not created, but this voltage or approximate value of this electric field is built in, it's created inherently. Okay, hence it is known as the built-in junction potential, built-in voltage, VBI. In other EE books, it is also known as, or it's represented as phi J. Built-in junction voltage, built-in voltage, or the Greek letter phi J. Okay. And the value of this depends on the material of the semiconductor. For silicon, it is approximately equal to 0.6 to 0.7 volts. For germanium, it's approximately equal to 0.2, 0.3 volts. Gallium arsenide and other compound semiconductors, it's about 1.1 to 1.5 volts, depending on what dopant impurity we use and what doping profile we use. Okay, but it's a material property. If you create a normal regular silicon diode, it's always between 0.6 to 0.7 volts. All right, so the equations for all three are standard, and I will break it down in the example on the next page. So everything to do with these three terms relates to the doping profile. So Na and Nd. And Na and Nd is a design parameter that is designed by engineers, depending on the application. Okay. So in a problem, Na and Nd are given, right? Na and Nd, the doping profile, the doping concentration is given. We are asked to determine the energy, the junction width, and the voltage. Okay. All three of them have standard equations. So E max, the energy, requires both the voltage and the junction width. right? It requires the voltage and the junction width. So we'll leave that for the last. Okay. We'll take a crack at the energy first and the voltage first. Okay. And leave Emax for the last. So VBI voltage is given by VT, natural log of NA/ND over NI square. So let's look at these quantities. NA and ND are given. NI is also given. VT is a constant. It's also given. Now, a quick sidebar about VT. I pointed this out. It's also known as the Einstein's relationship. It's a thermal voltage. It's pretty much a constant at any given temperature. So constant in the sense it's a function of temperature. It's KT over Q. T is the temperature in Kelvin. K is the Boltzmann's constant. Q is 1 unit charge. Typically, this value at 300 degrees Kelvin, not 300 degrees, it's just 300 Kelvin, turns out to be 25.8 millivolts. Sometimes see 25.9, it's rare, but commonly sometimes some books use 26 millivolts. I'm informing students right now, do not use 26 millivolts. Okay, calculate your own. This is a very common term that you will come across over and over again. So KT over Q, K is Boltzmann's constant, Q is 1 unit charge, T is temperature in Kelvin. Typically, I like to go like 3 or 4 decimal places, so 25.7999, like 4 decimal places at least. You can use 2 or 3, that's fine. It turns out approximately 25.8. Okay. So NA/ND is given, NI is given, VT is given. Simple plug and solve. So these equations, all 3 of them are simple plug and solve. So what I like to point out is the common places of error. Okay. The common places of error is basically Na and Nd are usually given as atoms per centimeter cube. So this is given simply as per centimeter cube. Okay. Ni also is atoms per centimeter cube. But there was an instance in one of the previous slides, it was per meter cube. I think the online homework, I think, had per meter cube. So I always like to convert everything to standard SI, meaning I get rid of all the unit prefixes and convert it to meters. So if it's micron, 10 raised to minus 6 meters. If it's centimeters, convert meters, 10 raised to minus 2. That way, that works for me. Something like this doesn't work directly for me. Centimeters, for some reason, my brain doesn't compute. Okay, so I always like to go step by step, and I always like to convert everything to meters, and then I perform my calculations. So NA/ND per centimeter cube, NI square is per centimeter cube, so it's divided by 10 raised to minus 2 times 10 raised to minus 2. Okay, so if you convert that, you have to be careful. It's per centimeter cube, so 3 times. Everybody understand what I'm saying, right? Centimeters, 0.01 meters, so 0.01, 0.01, 0.01 per meter cube. And then once you have VBI, you can plug it into the equation for the junction width, which is WD. WD again requires NA/ND. It also requires epsilon R and epsilon 0. Anyone remember what it stands for? In 215, did you talk about physical construction of a capacitor? Capacitance is given by epsilon A over D. Epsilon in further is broken down as epsilon R times epsilon 0 over D. The epsilon stands for permittivity of the material. So Epsilon in general just refers to permittivity. It's the ability of a material to conduct, sort of. Hence, permit. A is the cross-sectional area of the two plates of the capacitor. D is the distance between the two plates. And epsilon 0 and epsilon r are material properties. Epsilon 0 is permittivity of free space or vacuum. And epsilon r is relative permittivity of a specific material with reference to epsilon 0. Okay, epsilon 0 has units of farads per meter. So this is farads per meter. Epsilon r is dimensionless because it is a ratio. It's a ratio. It's a relative permittivity of any material with reference to epsilon 0. So it's a ratio. It's dimensionless. Okay, so that's what epsilon 0 and epsilon r. Epsilon 0 is a constant. Epsilon r is also a constant depending on the material you use. So for silicon, epsilon r is 11.7. And of course, this is a constant. Again, here it's 8.854 into 10 raised to minus 14 farads per centimeter. So it is 8.854 into 10 raised to minus 12 farads per meter. Again, just be careful about conversion. All right, and then it's VBI. So you plug in all the values, calculate WD, plug it into the equation for E, and calculate the energy or the electric field. Plug and solve. Okay. Let's take a pause. Let me know if you have any questions. Okay. So one note about this before we move on. Look at built-in potential. Silicon, right? Silicon is 11.7. So the doping profile is 10 to 16 and 10 to 17. Not very high, not very low, somewhere in the middle. But the junction built-in junction potential is about 0.78. And you can try the same equations and calculations by plugging in any number you want. Just plug in 10 to 15, 10 to 17 on one side. Just run that calculation, see what you get. So you can calculate the built-in potential for any doping concentration. Okay, and it simply be just plug in. If you create a spreadsheet with an equation, you simply have a bunch of values for different doping profiles. Okay, so what happens at the junction? We already saw why the junction is created. Now the goal is to, well, the goal is to actually conduct, right? So let's look at what happens when we apply an external field. In simple terms, what happens when you apply a voltage to this PN junction diode? Assuming everybody by now is familiar with the symbol for a diode. Yes. Arrowhead with a bar at one end of the arrow, at the tip of the arrow. That's the anode, that's the cathode. The naming convention is from, from the vacuum tube diodes. Some authors' books, instead of using K, use C. But if you see if you SEE see a K, it refers to the cathode. Okay. Sometimes you might see a C, but that C is also used for coulombs. It's also used for capacitance. So anyway, it refers to the anode and the cathode. Anode is the P-type material. Cathode is the N-type material. Now, if we apply a voltage to it, this direction, meaning a positive voltage of the positive polarity at the anode and negative at the cathode, they refer to this as a forward operation. forward. The application of a voltage is also referred to as biasing the device. We are setting up the device for operation. Hence, that procedure is known as biasing. So this is also known as bias, meaning forward bias. Okay. If you apply the exact opposite, we refer to it as reverse bias. Okay, reverse bias. And we'll talk about both in detail. Okay. So going from the N side to the P side, this is, of course, the electric field is in this direction, right? It's higher on the N side, lower on the P side, in that direction. Holes are on the P side. They have to climb, overcome the barrier, and go on the other side. Electrons must cross the junction, meaning they have to let go of some of the energy, but they also must be pushed towards the P side of the junction. Okay. In both cases, they are moving against the electric field in a sense. Okay. Sorry, not against the field. They're moving against their inherent property. They're moving against their inherent property. Holes want to move with the field. Electrons want to move against the field, positive and negative charges. But because of the nature of the construction of this device, the holes have to move against the field, which is the opposite of their inherent property. And electrons have to move with the field, which is, again, opposite of their inherent property. So an external voltage must be applied to impart sufficient energy so that they can cross over the junction. And so when we apply forward bias, actually, I'll come back to the slide because this right here makes it easier to explain. This is the anode. This is the cathode. Lots of positive charges, meaning holes here. What happens if you connect positive and negative here? What happens to the holes and electrons? Positive charges repel, opposite charges attract. So it's going to repel the holes, go in this direction. Same thing happens to the electrons. They're now moving towards the junction. But the junction is, let's just say 0.7 volts, for instance, right? So you apply an external voltage of 0.1, 0.2, 0.3, 0.4, 0.5 volts. You won't see much happening until you reach like 0.5 or 0.6 volts. Like after 0.5 volts, you'll see a slight increase in the current, meaning the electrons in the holes are acquiring sufficient energy to actually move through the junction. And after it crosses the junction, exponential increase in the current. Okay. And so application of positive charge at the anode and negative at the cathode allows the holes and the electrons to cross the junction. And we say that this is forward operation, forward bias. On the other hand, if you apply negative and positive, what's going to happen? It's going to attract away from the junction. So the carriers, the majority carriers, are going to be attracted away from the junction. So the junction is effectively increasing in size. Okay, because they're being pulled away. So the free carriers can be pulled away, but their corresponding ionized atoms stay in place. So effectively, the junction width is increasing. Does that make sense to everyone? Right? So effectively, junction width is increasing. Hence, we call it as reverse bias. So this is what happens to the majority carriers. Okay, this is what happens to the majority carriers. What about the minority carriers? When you apply reverse bias, well, whether you apply forward bias or reverse bias, minority carriers will behave exactly the opposite way. If you're reverse biasing this junction, electron is a minority carrier in the p type, right? Electron is a minority carrier in the p type. So the electron is forced towards the junction. And the hole is also pushed towards the junction. So the minority carriers in both cases are pushed across the junction in reverse bias. And so in reverse bias, a very, very, very small amount of current flows through. And the value is so small because of the very, very low concentration of minority carriers on both sides of the junction. Okay. All right, so let's go back to the graph. And we can see right here. So this is forward bias. In forward bias, yes, go ahead. Uh-huh. Okay, so the question being asked is, when we apply reverse bias, the depletion region increases. But if we take it away, does it go back to its original state? The answer is yes. Everything is a function of applying the external field, which actually, the overall goal is that we create these semiconductors so we can control their behavior, right? And so that's, if we remove it, then it goes back to its original state. So in original state, meaning no bias, we just leave it on the desk or on the shelf. The junction barrier just exists as it is. Okay, you're not applying any voltage. It's sitting in a box, sitting on my table, sitting in the lab, not applying any voltage. There's a junction barrier of 0.7 volts or equivalent to 0.7 volts. Because if you touch it, it's nothing going to happen. It's electrically neutral. Okay, so the junction barrier originally here, where you apply a voltage and it's going to drop, right? The junction barrier is going up this way. In forward bias, effectively, the junction barrier is going to decrease. But it's not actually physically decreasing. It's only allowing the electrons and holes to cross over. You're applying sufficient energy to those electrons and holes to cross over the junction. Okay, and when they cross over the junction, they are flowing through the device, and hence we say that current is flowing through the device. And we can control the flow of current by controlling the applied voltage. Okay. Reverse bias, exact opposite happens, increases the potential barrier because it's pulling everything away. And the reverse current, of course, is only due to the minority carriers. All right, so VI characteristic of an ideal junction diode looks like this. We spoke about this at the beginning. We apply a voltage. This would be approximately 0.6 to 0.7 volts for silicon. So this is voltage, this is current, so plus V plus I, this is minus V and minus I. Okay, so first quadrant is forward bias, third quadrant is reverse bias. You apply a positive voltage, you get a positive current. You apply negative voltage, you get negative current. The negative current is so small, it's typically around 10 raised to minus 9 to 10 raised to minus 12 range. And it is known as, excuse me, is known as the reverse saturation current because it reaches its limit very quickly. It only happens due to minority carriers, and the minority carriers are constant and fixed in number, so very small and fixed. Okay, it depends on the doping profile. Okay, so this equation that you see here is known as the diode equation. It is also known as the Shockley equation after William Shockley, one of the inventors of the solid state transistor. Okay, this basically provides a relationship between the diode voltage and the diode current. This equation, simply stated, can be written as ID equals IS into E raised to VD over VT. The N is the ideality factor. Typically, it's 1 for most normal diodes. VT is the thermal voltage. Excuse me. and VD is the diode voltage that is applied. Okay, so a specific voltage that is applied, you can use this equation to determine the current in that diode. Okay, so typically it reduces to IS into E raised to VD over VT. IS is a result of the doping profile, okay, the way the diode is created. And so it is part of the manufacturer's spec sheet. You should download the data sheet, which you would have done for the BAT54 last week. There is there'll be a value for IS in there. Okay, the value for IS. All right. Then, saturation current of a diode is solely due to minority carriers. Okay, minority carriers on both sides of the junction. And so it only depends on the properties of the minority carriers and the junction area. So there are a couple of equations associated with it, but this is just for informational purposes. So not something I'm going to assess students on the exam or the quiz or the homework. All right. So A is the area, the total junction area, Ni square, of course, is the intrinsic carriers. D is the diffusion constant, Ni square, Nd and Na are the doping concentrations. The D and L are the constants that we use for the equation, associated for the equations. But typically, I don't go through into much further detail than this. All right. There is further reading if students would like to do after these slides. So it's again, there are things that some instructors would want students to know of them, but I think it's better left outside. Okay, so this is an entire specialized field by itself. We can spend an entire semester delving into these, derive all these equations and everything, but it's a specialized graduate level EE class, EE 524. So someday it'd be offered, and if you wish, if it fits into your, I don't know, graduation requirements, you could probably take it. Anyway, the entire topic is very fascinating to me. I've spent a lot of my career as a student and as a educator on solid state and microfabrication and semiconductor devices. So I personally like it very much. But for the class, or for this class in particular, I'm going to stop and end at this slide. From next week onwards, we'll zoom out. Right now we are zoomed into the atomic and the subatomic level. Now we are going to zoom out because we've now seen what happens when you create a PN junction diode. So now we know the diode behavior. Now we'll build circuits with the diode. Okay, so applications, which is what this whole class is about. Applications and systems with devices. All right, so we'll end class here today, and we'll pick up here again on Monday. 2 announcements, one about the lab, one about the class. So no Friday quiz today. We'll cover some material again next week, and then we'll have a Friday quiz next week. But we'll have a Monday quiz as usual. That Monday quiz will assess material from this past week. Every single week when we have a Monday quiz, it'll always be for the past week. Okay, meaning if you are assessing quiz 4, then quiz 4 will assess material going back up to quiz 3. So on and so forth throughout the quarter. Second thing is about the labs, the pre-labs. So it took a while to get everything set up, but they are being graded. So it should be available to you by tonight or tomorrow, at least by Monday. But the point of giving an extra opportunity for students in the lab memo was that you would have lost points in the pre-lab, maybe not. But there's an opportunity to recover those points in the lab memo. Okay, but it does not affect the lab memo at all. See what I'm saying? There's just an extra opportunity I like to provide students so that they can recover some lost points in the pre-lab, but it doesn't affect the lab memo. Okay, so go ahead and say, if you have already not submitted, go ahead and submit your lab memos. And then it's not going to affect your lab memos at all. Okay, for the most part, pre-lab 1 was like spec sheet stuff, data, and so there's not much I mean, I've gone through and pretty much everybody has at least most of the answers correct. Yes. Yes. Yeah, at the end. I think I announced and explained that on each one of the lab classes. Yeah. So right at the end, you can just resubmit those again. Yeah. All right. Okay, we'll end class here today. If you have further questions, I'm happy to answer those before my next class.